The next problem I would like to look at is problem number 16. Same deal. I'm going to say, well, if this is Maclaurin, that's f of 0 plus f prime of 0 x to the 1 over 1 factorial plus f double prime of 0. The goal here is to be able to write any function in math as a power series. So, on the side, I'm going to say f equal the sine of x over 2 at x equals 0. This would be 0. F prime is 1/2 the cosine of x over 2. That would be 1/2. F double prime will be 1/4 negative the sine of x over 2. That would be a 0 at 0. The third derivative will be negative 1/8, or I should say 2 cubed. I shouldn't simplify if I'm looking for a pattern. This would be negative 1 over 2 cubed, maybe a few more derivatives. If I take the fourth derivative, I'll get positive 1 over 2 to the fourth sine of x over 2. When I plug in 0, I'll get 0. And the fifth derivative will be 1 over 2 to the fifth times the cosine of x over 2. And that would be a 1 over 2 to the fifth. Now, if I substitute these values in, that would be a 0 plus 1/2 x to the 1 over 1 factorial plus 0 x squared over 2 factorial minus 1 over 2 cubed x cubed over 3 factorial plus 0 x to the 4th over 4 factorial plus 1 over 2 to the 5th x to the 5th over 5 factorial, and the list goes on. So that is 1 over 2 times x to the 1 factorial minus 1 over 2 cubed times 3 factorial x cubed plus 1 over 2 to the 5th times 5 factorial x to the 5th, and the list goes on. That will be the series n equal to infinity. We always tie everything to the power of x. I notice the power of x is 135. That's arithmetic. So that is a sub n equal a sub 1 plus n minus 1 times the common difference. The first term is a 1, n minus 1 times 2. That is 2n minus 1. So an odd power is 2n minus 1 or 2n plus 1. And I noticed that the denominator will always have that factorial. Whatever the power is, the denominator will be that quantity factorial. And add to that, there is a 2 to the 1 matching the power, 2 cubed matching the power, 2 to the 5th matching the power. So for every term I see, there is a 2 raised to the same power as x. And now I'll check if I could start at 0. This wouldn't work. If I start at 1, that would work. And there it is. That would be the answer to this problem. So the goal here is to take any function that you see in math and write it as a power series. And I want to do one more, and I'd like to look at problem number 32. Find a Taylor series centered at A. Well, let's see how that works. And it's the same idea, really. If I take 32, the only difference here, you're no longer centered at 0, and let me remind you how this works. So, f of x equal 2 to the x centered at A, I would write this as I would say that is f of 1 plus, instead of f prime of 0, f prime of 1, x to the 1 over 1 factorial looks very close, except it's x minus 1. F double prime at 1 times x minus 1 squared over 2 factorial, f triple prime at 1 times x minus 1 cubed over 3 factorial, f 4 derivatives of f at 1 into x minus, and the list goes on. So again, I need to figure out what those are. The rest I'm going to copy down and try to figure out a pattern. I'll say, well, if f is 2 to the x at x equal not 0, 1, this is 2. The derivative is 2 to the x times natural log of 2. That will be 2 natural log of 2. A second derivative will be 2 to the x times natural log of 2 times natural log of 2 squared. That's 2 times natural log of 2 squared. The third derivative is 2 to the x times natural log of 2 cubed, evaluated at 1, that's twice natural log of 2 cubed, and maybe one more just for the heck of it. 2 to the x times natural log of 2 to the fourth. That would be 2 to the 1 times natural log of 2 to the fourth. If I fill in these blanks, I'm getting a 2 plus twice natural log of 2, x minus 1 over 1 factorial, plus f double prime, that's twice natural log of 2, x minus 1 squared over 2 factorial, plus f triple prime, oops, I got carried away there, plus twice natural log of 2 cubed, x minus 1 cubed over 3 factorial, twice natural log of 2 to the fourth, x minus 1 to the fourth over 4 factorial, and that would be the series n equal to infinity. And I tie everything to the power on x. That's a 1, a 2, a 3, a 4. So that is x minus 1 to the n. Very good. Now, I notice whatever the power is, the denominator is factorial. So 1, 1 factorial, 2, 2 factorial, 3, 3 factorial, 4, 4 factorial, n factorial. And I notice each of their terms will have, let's see, 2 times natural log of 2. 2 times natural log of 2, I messed up. There should be a 2 there. 2 times natural log of 2 cubed, 2 times natural log. So there's always a 2 natural log of 2 raised. And let's see, 1, 1. When this is 2, this is 2. When this is 3, this is 3. When this is 4, this is 4. When this is n, this is n. And now let's see where can I begin. Can I begin at 0? Meaning, if I start and plug in 0, can I get the 2? If I put 0 in there, well, let's see. 2, natural log of 2 to the 0 is 1. X minus 1 to the 0 is 1, and 0 factorial is 1, so it does work. I would start at 0, and that gives me the entire series. There are other ways of doing this, and we're going to really touch on those in the next section. Now, something that comes up in applications, you really don't need the infinite amount of those. Sometimes you just need a third or a fourth degree polynomial to really figure this out, and that's really embedded in the definition on page 638. And here they talk about polynomials. Let me get that in and read it really quick. So this is the actual applications of this. You really don't need all of these. Keep in mind those are decreasing. And factorial is growing very rapidly. Meaning when n equal 10, 10 factorial is a massive number. And remember that's in the denominator. So you really don't need to evaluate that far, especially if the number is around 0, if the number is a fraction. So what they say, let f be a function with derivatives of order k. If I want to find a Taylor polynomial of order n, well, what's n? Some number. That is f of a, f prime, so it matches, but you stop at n. So if I go back to problems number 1 through 9, which I skipped, it says here, find a Taylor polynomial of order 0, 1, 2, and 3 of f. Oops, that doesn't look good. Let me do it again. There we go. Much better. And if I pick a problem, let's say I'm looking at problem number 2. So, when they say find me a polynomial of degree 0, 1, 2, or 3, well, this is what I'm going to say. Since this is centered at 0, that's Maclaurin. This is going to be f of 0 plus f prime of 0 times x to the 1 over 1 factorial, f double prime of 0, x squared over 2 factorial, and no need to go beyond 3. That's all I need, because they want the third degree polynomial to be the highest. So I'll go on the side, and this is a lot simpler than what I did. The sine of x evaluated at x equals 0, that's a 0. F prime will be the cosine of x, that's a 1. F double prime will be negative the sine of x, that would be a 0. And the third derivative would be negative the cosine of x, that would be negative 1. So if I really look at this and figure out that sine of x is roughly around 0, 0 plus 1 x to the 1 over 1 factorial plus 0 x squared over 2 factorial minus 1 x cubed over 3 factorial. Now I would like, so when they want p sub 0, well, the term without any x is a 0, done. When they say find the first degree polynomial, that's 0 plus x to the 1 over 1 factorial, which is just x. When they say find the second degree polynomial, well, that is 0 plus x to the 1 over 1 factorial plus 0 x squared over 2 factorial. So the second order, the best you could do is get the 1 because the rest is a 0. And when they say find the third degree polynomial, you would say that is centered at 0 in this case, you would say that is 0 plus x to the 1 over 1 factorial plus 0 x squared over 2 factorial minus x cubed over 3 factorial. The third degree polynomial that approximates the sine of x is x to the 1 minus x cubed over 6. Around 0, this polynomial approximates that irrational number, or irrational function. And that's how this is really played. I would like to do another problem, but I don't know if I can pass 15. I am going to work out number 4 really quick. And I'm going to fly by it because if I pass the 15 by a lot, it won't let me do that. So this is going to be, again, like the previous problem. That's going to be f of 0 plus f prime of 0 times x to the 1 over 1 factorial, f double prime of 0, x squared over 2 factorial, plus f triple prime of 0, x cubed over 3 factorial. F of x is natural log of 1 plus x. At x equals 0, this is simply natural log of 1, which is 0. The derivative is 1 over 1 plus x, which is 1 plus x to the negative 1. At 0, it's a 1. F double prime would be negative 1 plus x to the negative 2. That would be a negative 1. F triple prime will be 2 times 1 plus x to the negative 3. That would be a 2. So this is a 0 plus 1x to the 1 over 1 factorial minus x squared over 2 factorial plus 2x cubed over 3 factorial. So to find p sub 0, that's p sub 0, that's simply 0. To find p sub 1, well, that is 0 plus x to the 1 over 1 factorial. The first degree polynomial that approximates this natural log is simply y equal x. If I go for the second degree, well, that is 0 plus x to the 1 over 1 factorial minus x squared over 2 factorial. And that would be